Okay, so this video is to walk you through the tracker software and just make sure that you know how to use it in the context of the projectile motion assignment. I know I posted a quick tutorial from somebody else I found on YouTube, but this would be more specific to your specific task. So you'll notice here that this is the assignment I've given you, and really we're looking at horizontal motion and vertical motion, and we're going to see if our graphs actually allow us to pull these formulas right out of the graphs. Basically, I'm asking, does real world data actually match what the physics of the equations suggests? Now, if you went and collected your own data, there's a few things to keep in mind. You don't have to. You could use some of the videos that I've posted, but if you make your own, there's a couple things that is good to use. Number one is to always use a high contrast background, so it's going to be easy for you to pick out the object from the background, and it won't blend in. Number two, don't throw the object too fast. When you're recording motion, if the object is thrown too fast, then it tends to blur in a video, and that means it's harder to pinpoint where it was in its position. The next is to not move the camera while recording. This is so critical. The video software doesn't know if it's seeing the ball that's moving or if the camera is moving. And as a result, you're going to get inaccurate data if you move the camera while it's tracking the ball. The next thing is to make sure you have a measurable item in the video. It could be a meter stick if you have one, or as long as you know how big something is. Even if that meant you know exactly how tall you are in meters, then you could tell the computer, this is me standing in the video and this is how tall I am. Because the computer doesn't know if we're looking at, let's say, a ping pong ball that's really close up or a basketball that's far away. So it needs to know how big things are so it can scale the data appropriately. And of course, the last two things is to make sure that you're throwing your object perpendicular to the camera shot, and finally that the motion goes from left to right. That only makes sure that the motion is in the positive direction because it's moving to the right, as opposed to throwing a ball from right to left, which means it would be in the negative direction. So, assuming you've downloaded the software okay and you've watched the tutorial, let's just do a quick walkthrough of what I'm expecting you to do. Really what it says here is use the software to create the following graphs of your data. We want a position in the x, position in the y, velocity in the x, and velocity in the y. So here's the tracker software. I can open up my video by clicking open, and it'll bring this box for searching on my computer, or alternatively I actually have the video here in a separate window and I can just drag it over and drop it in. So this is what the video looks like if we quickly play it through. One of the things you'll notice is it takes a number of seconds before the person actually throws the ball. So I'm not really interested in any of the data that comes before that. So what I need to start by doing is going up to the video settings, and I just notice here that the ball was thrown at which frame? Let's say that's the first frame where it leaves the hand, so at frame number 77. So I'm going to go to the video settings across the top and tell the computer, don't worry about anything before frame 77. That's the first one that's of importance. The next thing I knew is to specify how big things are. So I have this object, this option here to create a new calibration stick. I'm going to bring it over here to my meter stick. Just like that. I'm going to tell the computer that what I'm looking at is 1 meter. I literally just push the button 1 and enter. The next thing I want to do is create a coordinate system. By default, it puts it in the middle, but this is not a good place to start your coordinate system because it means that the ball's position starts off negative, and as it moves through, it goes into positive. And it would be nice if we just had the ball's position at the 0 mark and that it moved in the positive direction. So first thing I want to do is I want to drag this over so it shows it's the beginning of where the ball is. So the ball is beginning just inside the positive mark. It also makes sense to have your horizontal line actually line up with the ground, since that would be the measurement of how high the ball was off the ground. This would be an actual measurement. So I've put it here at their feet. You'll notice that their feet don't quite line up. Maybe that's because their ground is slightly slanted, or maybe the camera was slightly slanted, but you can actually tweak that a little bit by grabbing out here and line it up so that this is telling the computer what horizontal is supposed to be. Now, what we want to do is to start analyzing this object, and that's as simple as clicking Create Point Mass. I can change the name if I like. Let's call this basketball. And what I want to do is analyze the motion of the ball. And I can do that simply by clicking the Shift button on my keyboard. Right, you'll notice here that the arrow turns into a little crosshair. And what I'm going to do is to tell the computer, here's where the ball was, and it's going to advance to the next frame. and I'm going to go through it fairly quickly. You would be going through in a lot more detail, making sure that you are trying to touch the center of the ball exactly every single time to make sure that you have the best possible data. But I'm not going to worry about that because this is just an example. Okay, so we have the ball coming back down to the final frame. Okay, and you can even see here, just look at noticing where my stick originally was, that this camera has shifted slightly. So these people actually, when they were tracking the motion of the ball, the camera actually shifted a small bit, and that's going to affect our data in small ways, but interesting to notice. Additionally, if you needed to, you could actually zoom in so that you could have a higher resolution of the picture. If that's something you needed to do, make sure you do that. So what we have here is data on the right hand side, and it already has plotted the graph. This is a graph of X position versus time. We see a fairly linear graph as the ball moves from the person on the left to the person on the right. I can actually change here by clicking to Y position. So this shows me that over time the ball was taking big jumps in the Y position at the beginning, and was taking smaller and smaller jumps as it slowed down, and then it came down the other side, started to take bigger and bigger jumps as it went faster and faster. And the last two over here are X velocity and Y velocity, so I can actually show what those graphs look like as well. So those are the four that we're going to need to capture. So let's go back to X position. What I really want is to know the equation of this graph, because I'm trying to see if the equation of this graph, the velocity or the X position versus time graph, would give me a similar equation to this, which is also an equation for X position versus time. So what we want to see is if this graph actually can produce this equation. So we're going to do that by right-clicking on the graph, and we're going to analyze. And you'll see here, this is just another view, but what I want to do is analyze the curve fits. And so it's going to put a line of best fit through my data, and it's going to tell me what the values of that equation would be. So for example, they're saying the equation, if it was X equals AT plus B, then it would tell me that my A value is 3.6 times 10 to the 0, so basically just 3.6. And the B value would be 8.47 times 10 to the negative 2, so basically 0.084 is what goes over here. So let's rewrite that. Let's actually keep those values in mind, and I'm not going to keep it as with X and Y values. I'm going to call them, I know my X is actually position, so I'm going to call that D. Let's do that over here. So we have displacement in the X direction equals, and what did we have here? A times T, so 3.604 times time plus 8.471 times 10 to the negative 2. So we're going to have 0.08471. Okay, we'll change that back to a little letter D. Okay, so that's technically the equation of that graph. And if we go back over here when we're doing our analysis, this is kind of the last thing I want to mention here. One of the things it says here is to write down the equation for the graph, and then it says you can ignore the plus number at the end of the equation. Well, let's look at that again. So we have produced this equation, and I'm telling you you can ignore this value. All right, and the reason you can ignore this value is that based on the mathematics, this number simply comes from where you originally put your coordinate system. Okay, and if you go back to the beginning of the video, it's only because if we could actually put this directly on the 0 mark, then we would have no value here, because it would be plus 0. There's no transformation to it at all. But of course ours, it's very difficult to put it exactly at 0, and so we're going to end up with a small number at the end. And what I'm saying is, don't worry about that. It doesn't matter exactly where you put your coordinate system, and you'll notice that this value is incredibly small anyway, and so we can basically ignore it, in which case when we go to do our analysis, let's just ignore that part and call this the equation for horizontal motion. Now the same would be done as you move through the assignment for your Y position and your X velocity and your Y velocity. The only point I want to make that's a little bit tricky when you go to X velocity, if you go to do your analysis, you tend to see here, let's get rid of the first one, We're not interested in that first data. We tend to see that it tends to bounce around a lot, but really it's not actually bouncing around that much. You notice that these aren't very big differences in numbers. At the most, it's just over 4, and at the least, it's just under 3. So what we ideally want to do before we get this equation is to show a more accurate scale. And I can do that. Notice here when I hover over the numbers, I have the arrow up and down. That allows me to move things around up or down. But if I go to the very near towards the top of the numbers, there it is, then I only see a half an arrow, and that allows me to determine the scale a little bit, okay, to shrink things up or down. Okay, and now here we can see that by and large the x velocity is all bouncing around that same sort of number. So although the data tends to bounce around a little bit, I don't want you looking at that data and thinking, oh my goodness, the velocity is so dramatic, when really if you look at the scale that's been presented, it really isn't all that dramatic. It's just bouncing around the same number. So keep that in mind when you create your graphs and when you talk about what the actual equation is. The last thing you're going to need to do, and this is something I didn't mention in the first part, is you want to get this picture, because I want it as part of your actual lab report. So please make sure that you get a copy of this picture. You can use any screen capture software you want, or if you right click, you actually get an option here just to snapshot it. And what it does is it creates a little snapshot over here that then can be saved in any of these image formats, and you could even copy it and then paste it into a Word document. So there we have it. And I know I don't need to remind you of this, but although this is a complete graph, it doesn't have good descriptions. We need a title here. You should put in something to describe what the axes are. So if you can edit this image in any way, or at least put some information in text boxes, you could insert text boxes along the bottom and put in a better description of what these axes represent and what the line is actually called. So use that kind of those feature editing to make sure that you're actually displaying your graph properly and that it's not just a bare graph, because that's incorrect. Okay, so best of luck with that. I think that you'll be able to work your way through those questions, and I think this is a great example of how we can actually use real life data and track it so that we get something that's more authentic rather than simply looking at fake data that can be created by any computer. So best of luck with